ask in the chat if possible. So, welcome to this week's Q&A session, and as always, we'll give an overview of the important lectures from last week, so the most important things you should maybe take a look at again, and just to recapitulate what we've been discussing in the previous week. So in lectures 3 and 4, we've been discussing first challenges and tasks of an operating system, and then we took a detailed look at processes. So in challenges and tasks of an operating system, we took a look at abstractions that an operating system provides, tasks of an operating systems and related problems and challenges. And in processes, we started looking at the Unix process hierarchy. We had a closer look at the Unix shell and how it handles processes, and also especially input-output and input-output redirection. And then we took a quick look at the Unix philosophy, at system calls for process creation, and some details of Unix processes. So for operating systems abstractions, we've seen that one of the most important abstraction of an operating system is a process. And so we've seen there are different definitions of a process, and one that's pretty short and concise is a process is a program in execution. So on the one hand, we have programs, which is just what's on disk, an executable file, an hexa file on Windows, an ELF file in Linux. And if we start this program by entering its name in the shell or double-clicking the icon, then we create a process out of that program. And of course, in Unix, you can create several processes out of the same program. So you could have several terminals open, which are all the same program, or you could run several GCC compilers at the same time. And to be able to administer processes, the operating system needs context, and this context is stored in a data structure inside of the operating system kernel called the process control block. And this especially contains information for all the times a process is not running. So it contains information about the state of the CPU, about the memory that's allocated to the process, about the files which are opened and which position in the files the last read or write operation took place, and some meta information like the owner of a process, the current mode, and so on. And we've seen different process models. So we've seen multi-programming, concurrent processes, CPU multiplexing. So it's all a different view on the same thing that happens, which is we're just sharing our one piece of hardware, like our one processor, our one main memory, our one set of IO devices among multiple activities for which we at least create the illusion that they take place in parallel. But you've seen a CPU on a single processor system, single core system, can only execute one instruction at a time. So the operating system has to create the illusion of things happening in parallel by just rapidly switching between the different processes. So you as the human user usually don't notice that something else is happening in between. And then we took a look at process states and how you can transition between different states. So we've seen this very basic model that a process can either be running, ready, or blocked. And we took a look at which transitions are permitted, which cannot be permitted, and why. So in a basic model on a single core, single processor system, you only have one running process because there's only one CPU executing one instruction at a time. And this is always belonging either to a process or to the operating system itself. We have a number of ready processes, which are just waiting for the CPU to become available. And we might have a number of blocked processes. These are processes that initiated an IO operation, which is still running. So they cannot continue running until this IO operation has finished. And so we have these transitions. So we can go from ready to running when one process gives up the CPU, either voluntarily or involuntarily by being kicked off the CPU by a scheduler. We can go from running to blocked when a running process requests an IO operation. And we are going from blocked to ready when this IO operation is finished. What's important is we are not going from blocked directly back to running when an operation is finished, because that could create unfairness, because then a process just initiating lots of smaller operations, one after the other, would just be reactivated immediately when the IO operation is finished. And of course, that's not what we want, because then this would be a denial of service attack on the CPU power of our system. So we took a look at CPU scheduling, and we mentioned process synchronization and inter-process communication, which are also important methods for the operating system to coordinate activities. And related to this, we also took a look at the memory hierarchy. So we've seen that in order for the memory to keep up with the CPU speeds, which are increasing much faster than the memory speeds, we have to introduce what we call a hierarchy of memories. So we have very fast memories, which are as fast as the CPUs. So the CPU registers, for example, but these are very expensive to build, and they need lots of space on a chip. So there are only a few of them, the CPU registers, like maybe 32, 64-bit values. Then we have memory, which is a bit bigger, several levels of our cache hierarchy. So each level, so the L1 level is small and very fast. L2 is quite a bit bigger, but slower. Then there might be a level 3 cache. And then finally, we have our main memory, our RAM, our DRAM, and this is very slow. So it takes maybe more than 100 CPU cycles to retrieve a value from RAM. So if the CPU would always have to wait for the RAM to deliver data without any caches in between, then our computers would be much, much slower, because the RAM just couldn't keep up with delivering data and instructions fast enough. And then finally, of course, you have disks or SSDs nowadays, which are still an order of magnitude slower. And our operating system has to at least manage RAM and disk, whereas registers, the allocation of registers is usually handled by the compiler when code is generated, and the allocation of cache usually happens automatically. So that's what's going on internally in the CPU, and the operating system is usually not concerned with this, though the operating system can, for example, clear a cache when some context in there or some content in there is actually outdated. So a major task of the operating system concerning memory is the main memory management. We've seen virtual memory. So for virtual memory, we create the illusion for each process that it may use the whole memory of the computer. But of course, if we give all processes each the whole memory of the computer, we would be running out of memory. So virtual memory is a method to translate addresses generated by processes into physical addresses in the RAM. And also, when we're running out of RAM, to maybe put some of the currently unused or data we use later or code out to disk in a so-called swap space or swap file. So we have more space for processes that currently need the memory. And virtual memory also is used for protection. So we can add protection information like this. Memory is only readable or writable, or we can execute code in this region of memory. We'll take a look at memory management in much more detail later. And of course, considering storage space, the operating system has to manage the disk. So we've seen the basic functionality of a disk, which is just a bunch of blocks of the same size. And in order to make it more accessible for processes and for the users, we create yet another abstraction, which is a file, and files contained in file systems and directories. And these then internally map to just regions of blocks which belong to this file. And again, we can have access control. We've seen we have file owners, and we have access permissions like, again, read, write, and execute now for a file on a disk. What else do we have? Well, we have a number of challenges. So modern computer architectures are no longer the simple machines from the 1980s. They've become much more complex. So today, almost every machine, even small embedded systems, have multiple CPU cores. So the operating system has to enable load distribution, has to enable a good utilization of the hardware that's available. We might have non-unified memory access in larger servers. So we have multiple physical processors, and each of these processors has its own memory attached. So reading, writing data from memories attached to other CPUs is slower. So it has a higher latency and a lower throughput. For cloud computing nowadays, we need hardware virtualization. So we want to share one physical computer among not only different processes like an operating system, but we want to share one physical large computer between different operating systems running on top. And each of these operating systems, as usual, has lots of processes running. And maybe these operating systems are belonging to completely different customers of the cloud provider. So you have to enable or ensure very, very safe protection boundaries between these systems. And of course, cloud computing uses this to provide services. And of course, we want these services to be highly available and adaptive. You don't want your cloud provider to go down every couple of hours because, well, you have some important stuff like your online shop running on it. So we then took a closer look at the Unix process hierarchy. So we took another look first at the simple process state diagram with our 3 states ready, running, blocked. And then we took a look at the features of the Unix process hierarchy. So at process identifiers, so just a number uniquely identifying a process at any moment. But as soon as the process terminates, this number can be reused. We took a look at how processes are created in Unix. So the process inheritance, so parent-child processes, and a very special process, the very first process that's run, the so-called init process, and what it's doing. And related to this, we took a look at one of the most important programs in Unix, the shell, and how this handles, in general, input handling, starting jobs, controlling jobs, and so on. So we took a look at how shell commands are formatted. We took a look at job control, so to terminate, to continue jobs. We took a look at how to combine Unix processes using I/O channels. So we've seen standard in, out, and arrow channels, and especially also how to redirect I/O to a file or from a file instead of the keyboard and terminal, or also how to combine several commands into one more complex command using pipelines, which combine the output of one program and send it to the input of the next program in this pipeline. Then we took a quick look at Unix philosophy. So Unix philosophy can be summarized as do one thing and do it well. So Unix was built using a set of small programs that are designed to do a single task. So they're easy to understand and to debug. They're easy to use, and you can combine them flexibly by sending data from one process to another. You might wonder if this is still the case today. So if you check the help output of the ls command, you see, I think they used almost every character available in the alphabet and then some more as options for ls. So it's debatable if it just does one thing and does it well, or if it just does so many more things that usually ls shouldn't do. But that's the thing with software everywhere. It's just growing in features, it's growing in complexity. So maybe returning to some simpler things might be interesting. Nevertheless, what's one of the great ideas in Unix is that processes are designed to work together. So I can use a process, run a process, use its output, and just hand it over using a pipeline to the next process, which can do stuff on this. So I can grep for certain lines, and then maybe I can change the contents of these lines with another program to uppercase, and then I can reverse the sorting of it and stuff like that using pipelines instead of writing a new program for doing it. And pipelines are useful because without pipelines, you would have to save the output of the first process in a temporary file and then read this file in the second process, and so on and so forth, and remember to delete all these temporary files later. And pipelines just do this automatically, so there's no intermediate files involved. The output of one process is just handed to the input of the next one. And this is enabled by just having a very simple input-output format. It's just streams of characters, so there's no formatting involved. There's nothing involved, it's just streams of bytes. And this is a simple but very universal interface to exchange data between processes. It's debatable if this is good enough for today's requirements, where you might want to send a video frame or a picture or some audio or stuff like that, which has some format. People are discussing stuff like this. Microsoft is trying to invent some sort of object model between processes in the PowerShell for Windows. So let's see how this is going. There was actually an interesting talk last year, and I can probably put the link to it on the website, about what's the next 50 years of the Unix shell. And this is very worthwhile. You don't have to watch it. Obviously, it's just for those of you who might be interested, maybe some nice additional stuff to look at. Well, then we took a closer detailed look at process creation and the system calls. So a system call looks like a regular function call if you write a program in C, for example, but essentially they create a transition from what you execute in user mode as your program to a functionality that's implemented in the kernel. So the kernel has more privileges. It has access to all hardware your process doesn't, for example. So essentially we have to make this transition in order to enable the kernel to do its functionality. And of course, we have to be able to control this transition, because otherwise we would be able as a user program to execute arbitrary kernel functionality, which would be a large security problem. So there's a question in the chat. Is there a particular reasoning behind Windows systems not being based on Unix when essentially every other system in existence is? Yes, there is a reason. But it's mostly an economical reason. So Microsoft in the early 1980s was the biggest Unix vendor on earth. And most people don't know this. So they had their own Unix version called Xenix, but Unix was very expensive to license back then. So Unix license cost several $1000s. And Microsoft wanted to do something new, and they had MS-DOS, obviously, in the 1980s, and then they joined up with IBM to build a nice new real operating system called OS/2, so the second operating system. And then Microsoft and IBM had very different ideas of where to take this. And so IBM continued to develop OS/2. OS/2 is mostly dead nowadays. And Microsoft just first continued with a graphical user interface on top of DOS. Well, that's what Windows was until Windows 95, 98 ME. But in the early 90s, they started redesigning their system from scratch, from the ground up. And they hired a person called Dave Cutler from a company called DEC, and he was an experienced operating system developer of a competing product to Unix called VMS from DEC. And so if you look at the old VMS system manuals, you see Windows NT. So the new system NT stands for new technology. So the system that all subsequent Windows versions like Windows 2000, XP, Windows 7, Windows 10, 11 are based on. Well, these look very similar to VMS in their basic structures. So it was essentially that they hired someone who did not come from a Unix background and asked this person to write a new operating system. So essentially, that's the reason for it. You can actually run Windows applications on Linux using Wine, which is just emulates Windows library calls. It doesn't work perfectly, but it works for an amazing number of applications, even some games nowadays. So I hope that answers your question. So so we have this transition from user to kernel mode, and this is a control transition. So we have to use system calls to do this transition. And otherwise we cannot use kernel functionality. So this control transition essentially then transfers the CPU from this user mode, where the CPU is restricted in what it can do. For example, it cannot disable interrupts in order to, so you cannot, for example, disable the timer interrupt. This would hinder the scheduler from running. And this switches the CPU to the system mode or kernel mode. And then the first thing the operating system is supposed to do in kernel mode is check if this is a valid system call, if all the parameters are correct, if the process is actually allowed to execute that system call, and then it will be executed. And after it's executed, the system will return to user mode. And we took a look at system calls for process control. So how to create, destroy a process, how to wait for the termination of a process, how to terminate a process when you're a process yourself, and how to check the status of processes. So the first thing we took a look at was the fork system call, and this is a very specific thing in Unix. So fork is the process call to create Unix processes, and originally was the only one. So this is called once, but it returns twice, because when you call fork, you switch to system mode, the Unix kernel then copies all the information of the process that calls fork into a new process, and then returns from fork in the original process and in the newly created one. So when you call fork, you have an almost identical copy of the process that called fork. There's one exception: the process ID and the return value that fork returns. And this might be important for the theoretical exercise if you check this out. What's originally done is that code and data is shared between the parent process, who called fork, and the child process, which is the newly created one. And we've seen this uses a mechanism to improve efficiency, which is called copy on write. By the way, if you look at that blue box on the slide here, so we usually give a number in brackets after naming a system call or a library call in the C library. And this just indicates the section of the Unix manual that this is in. So, for example, there's exec, which can be used in the shell, which would be in section 1, or used as a system call, which would be in section 2. So this makes it clear which section we are talking about. For example, a shell command or a system call. So we've seen details of process termination. So exit, the function that never returns. So that's the way to terminate the process itself. So a process can say, I want to terminate. We've seen what happens with so-called orphan child process. So when a process creates a child process, and then this process that created the child process, the parent process, either dies or calls exit. So then we have some gap in our process tree, our inheritance tree of the processes. So that's when we see the init process coming in and taking care of what we call the orphan child processes. This all sounds a bit rude, right? It's its old terminology. We've seen process interaction, so we've seen the function wait to wait for termination of processes, and we've seen what's a zombie process. And then, of course, we've seen the problem like, okay, we have fork, so we can create identical copies of an existing process. But this would mean like, how can we start a new program? And so in Unix, this functionality is separated. So we not only have fork, but we also have exec. So a new process is started by calling exec. And where we want to keep the old process running, we run fork. And then in the new process, the child process, we can then run exec to start a new program. Yes, there's another question. Did fork return 0 in the child process and the child's pit in the parent process? Yes, exactly. So that's one of the differences. So the child's pit is returned in the parent process because the parent needs to know which pit the child has, and if the child needs to get its own process ID, it can just use another system call called getPit. With getPit, you just get your own process ID. So whenever you get a 0 returned, you know you're the child process, and there's no process with the number 0 in Unix usually. Like there might be exceptions in macOS 10, for example. There's another question: exec never returns. Yes, we had this discussion before. So exec can return. Exec can return if there's a failure. For example, if you try to exec a program which doesn't exist because you have a typo in the name, or it can return if you have no permission to execute, or if something else has gone wrong, like you ran out of free processes or out of memory or whatever. So if all goes well, exec never returns, but you should actually still check for errors just in case one of these exceptional cases happens. So exec can return, but exit to exit the program. I've checked this again. Exit in most Unixes can never return. So an exit from a process cannot be called or go wrong, but exec could return. All right. I tried killing the init process in a VM as you suggested in one of the videos, but nothing seemed to happen. And I tried Googling it, and it looks like the init process is protected from being killed. So Just killing it means, so kill is a command that's a bit of a misnomer. So kill, we'll talk about this later in the course. Kill is a Unix tool to send a so-called signal to a process. So a signal is just a number between usually 1 and 31, but it could be higher in 64-bit systems depending on your Unix. And one of these signals is what we call uncatchable. This is signal number 9. So if you try kill -9 process 1, it might be killed. Yes, that's what you did. Then I guess it's protected. What a shame. I haven't tried this for some time. So that's a shame. So in early Unix systems, actually, if you there's a functionality initiated by init, like starting some Unix daemons in the background, so some Unix services. Back then, you actually also caused init to reload these. So these are configured in a text file by sending a signal -1 to 1. So this just sent a signal to init to say, yes, please reload that stuff. And if I accidentally actually mistyped it to kill -9 because it was my fingers, and I shut down the complete system. Now, the problem is there were 50 users using that system at the moment, and that didn't make anyone happy, I suppose. Yes. Well, I was a young student, so I needed the money. Right, good questions. So when we want to execute another program, we use one of the system calls from the exec family. We've seen different ones. Actually, these are all just in the C library, so these are not actual system calls, but they all just do some handling and then refer to the same exec sys call, which is the actual kernel calls. And then we've discussed how to combine fork and exec to actually start a new process from a new program binary. And finally, we took a look at a more realistic Unix process state diagram, which gets more complicated, but you don't need to know this by heart. Yeah, that's a finger slipping from 1 to 9 is impressive. I think that wasn't just the finger slipping, but just usually you type kill -9 to get rid of something and not -1. And if this is in your mind and you don't really take extreme care, that might be a problem. So exec, that's an interesting question. Exec puts the current process in stasis on an unused thread while creating a new process. That's a question. No, what actually happens when you call exec is that the process calling exec, in this process, the operating system replaces the whole memory contents of this process. So all the program code and all the data with what it's loaded from the parameter of the exec, so the new program you want to start. So there's not an additional unused thread, it's just a handover. So when you call exec, you're in the old memory contents of that process, and when you return, well, when exec returns, well, it doesn't really return, but it starts this new process, but the process ID stays the same, which is interesting. So it's just replacing all the contents of that process. That's a bit of a strange thing at first, to be honest. What happens to the old process? It stays the same process. That's the interesting thing. It's just a completely different content. It's like the same box outside, but you put something completely new inside. And you start it from scratch because there's no point to continue. Yes. Oh, we can maybe have an exercise, or I can do a bit of a live demo next week to show you some insights. I'd have to prepare something to show you what it looks like in the kernel. Right. So how do we continue with the course? You've probably seen the first theoretical exercise was handed out on Friday, and already got the question of, I can't hand it in. Yes, right. So Espen should have opened the submission on Blackboard, and please try to send all organizational stuff, like if you still want to change a group or something like that, to him. And we'll discuss it internally, because I'm happy that he takes off some work from my back. And if you want it commented, well, we don't do grading, but we give feedback on it, you please submit it by this Friday, so whatever, midnight. That's fine. Please, for now, submit it in groups if possible, because we don't know how many of you are going to submit these exercises. Just a reminder, these don't have to be submitted. So essentially, we need to see how many of the answers are actually coming in, because that's like if 430 of you submit the solutions separately and want some feedback, that'll be a bit of work, to be honest. So the first practical exercise will be on the website right after this session here. And as you've seen, this is mandatory. So the handout is today. Submission deadline is plus 3 weeks. So Monday in 3 weeks at midnight again. And this is about what we've seen in the last lectures. So mostly about fork and exec and a bit more how to use this. So essentially, you're going to build an alarm clock in Unix. So an alarm clock sounds pretty simple, but you learn how to work with Unix processes, you learn how to work with time. Time in computers is an extremely complex subject. And of course, we'll give some hints and things next week. So you have some time to look at it, you have some time to experiment, and I'm looking forward to your feedback if you like the task and how complex it is and which problems are showing up. So where can we find the exercise questions? In, well, right after this session. So it's all linked on the webpage. So the webpage is, I can post it again. Yes, just a second. There's that one here. And there's links, just the practical exercise isn't on there because I'm just posting it right after this session here. All right. So we'll give more hints and a bit next Monday on. So you have some time to look at it. I would really recommend starting looking at it early because it's more work than you can probably do in half a day just before the deadline. And of course, you should submit it in your group. So the theoretical exercise number 1 was concerned first with Unix process and shell. So we were revisiting the init process and its role. I wanted you to do some reading of man pages to practice how to find relevant information in the Unix system and to think a bit about the behavior of shell commands. Then an interesting thing about forks. So you can create as many new processes as you want as a user, and that can create problems. So I had an example of a one-line piece of code that might be problematic, and your task is to figure out what it's doing. So there you should probably think about the return values of fork. And then the process execution, there was an order. The order wasn't relevant here, so it's about the parent-child process relation. So a bit of a riddle to figure out like how many processes were created there. So this had nothing to do with order. That was just a copy and paste error from an old headline. And the practical exercise, as I said, is you're supposed to build an alarm clock, of course, using Unix system calls like fork, exec, and wait. So time is a very complicated subject in Unix. And of course, it's probably your first complex and maybe even somewhat useful C program. And we've designed it in some smaller steps to enable you to do it one piece at a time. Could you show us where on the website they can be found? I have some problems finding them. Yes, just a second. So, so the forum question we have asked around. So Piazza is getting more and more expensive, especially for this course size. And some colleagues also in one of the ED courses and the math departments are using Discourse. So TDT4186, I think, has used it already, Algdat. And Discourse can be also rented on their service, which might not be GDPR compliant, but it's an open source system. And we're currently trying to figure out how to set it up on our own server so we can make it available to you. More on this later this week when we have figured it out. This is not as easy to do from Sweden as if I was sitting in Trondheim. But we will try to get to work this week so you can ask questions about the exercises and lectures there. Sorry for the delay, but at least we seem to have found a solution now. So Okay, that's all on the slides. So I'll just show you where to find things in a second. So this is the web page, and there's this just list and calendar, and this shows the handout here, handout theoretical exercise 1 processes, and then on the right hand side you see the PDF with the theoretical exercises, and the practical exercise, a new one, will just appear below the link for the live session just after this session. So I'll upload it and link it there. And if you can't find the URL, drop us an email and we'll send you the URL. I want to avoid also uploading that stuff to Blackboard, because then you have 2 copies of this and that might be confusing. I want to keep most of that stuff actually together on that page here, because it's, for me, it's easier accessible and it's just more simple to do than all that Blackboard stuff, especially since they introduced 2-factor authentication. All right. So that's all from my side for today. Somebody's starting to vacuum clean here around here, so it might be a bit noisy. So are there any further questions? If not, well, you know how to reach us. Otherwise, thanks a lot for joining today. I hope you found it interesting, and see you again next week. And we'll send an update via Blackboard announcement about the forum solution as soon as we got it to work. All right. All right. Are you still a counselor for Master thesis this semester? Yes. So this is a question. We are not sure what's going to happen next semester. So that's the reason why I'm currently traveling. So I was in Germany last week, but we can probably take this off the recording. Also, I'll stop recording.